Welcome back to our series on applied regression analysis. I'm Mark Ledbetter, and this is lecture video 12, Review of Basic Statistics, our final part, part 8. And if you're watching this in the fall of 2020, I made a mistake on the course calendar, so I will correct it. This was supposed to have already been chapter 5, but we'll do that next time. We're going to talk about something that's very important: error rates, power, and sample sizes. So, some of this will be a review, some of this will be new to you. So, when we're looking at error rates, we are looking at the outcomes of our hypothesis test right here. And so this is what we call an error table. Over here is the actual up at the top, and along the left side is the decision that we make. So, if I have H naught here, that means that I fail to reject H naught. If I have HA, that means that's the alternative hypothesis. That means that I have rejected H naught in favor of HA. So we have this truth table here, and so if we make the decision that, we'll look at the top line first, that we fail to reject H naught, if H naught is true, then we've made a correct decision, no error. So no error here. And the same thing here. If we decide that we reject H naught, so HA is true, and it really is true, then there's no error. So the type 1 error is when we make the decision to reject H naught here, but H naught is really true. So that's type 1 error, and we usually use alpha to denote type 1 error. You've seen that when you've done hypothesis testing and when you've done confidence intervals. So the type 1 error is the probability of rejecting H naught given that H naught is true. So this is a conditional probability. By the way, unfortunately, the book is quite wrong with this table, how they describe some things, so please use this video instead. All right, for the details. And if we fail to reject H naught, but H naught is not true, in other words, the alternative is, that's called a type 2 error, okay? Now, if we reject H naught when H naught is false, in other words, maybe I should change color here because it's just not helping at all at this point, is it? So I've marked that we have power of the test, and that is when we reject H naught and we should. In fact, HA is actually true. Then that is the power of our test. How often do we reject H naught when we're supposed to reject H naught? Okay. Oh, and I said earlier it was a truth table, but it's really not a truth table because these are conditional probabilities. All these are conditional probabilities. They're not just probabilities. Okay. So, type 1 error, the probability of rejecting H naught given that H naught is true. It's a false positive decision. So again, it's a conditional rejection here. So we're saying the probability that we reject H naught given that H naught was actually true. So this is the type 1 error, and again, alpha. So now, here we have a table, and I want to show you how it works. So here's our decision over here, and here's the truth over here. And in this case, we say that H naught is actually true. When H naught is true, we can either fail to reject H naught or reject H naught. Notice that these add up to 1. Okay? But notice that these are greater than 1 here, the top row, and this bottom row is less than 1. A truth table, both columns and rows, the total in the whole table over here would be 1. Okay, so we would have to have a 1 here and a 1 here. Actually, we wouldn't have a 1 here. If this were a truth table, then we would have to have 1s for all the marginals there. And that's not what we have. So it's not a truth table. It's a conditional probability table. And then under the fact if HA or H1 is true, notice that these add up to 1. Okay? So we have when it's given that H1 is true, we can either fail to reject H0 or reject H0. Okay? So if we want to find the probabilities over here, the probability that we fail to reject H0, given that H0 is true. So fail to reject H0 is this row here, fail to reject. Given that H0 is true, that's 0.95. Now, let's skip down to the third one. Fail to reject H0 when H0 is false, that's going to be 0.20. That's this other value here. And now we, type 1 or type 2 error. We'll get to that in a minute. So now let's look at the probability that we reject H0. Okay, so that is now the lower one. We're now on this row. Given that H0 is false, that would be this value, 0.80. And now we're going to drop down to the fourth one, the probability that we reject H0, same row. Given that H0 is true, that's 0.05. And now we want the type 1 or type 2 error. That means we need to add the type 1 and the type 2 error. So that's going to be, this is going to be type 1, and this is going to be type 2. They're along the diagonal here, so that's going to be 0.05 plus 0.2, which is 0.25. Type 2 error now is the probability of not rejecting H0 when H0 is false. Okay? All right. Now, so let me now put this in symbols that we've used before, or some of them anyway. So as I pointed out earlier, this, when we reject H0, but H0 is true, that's a type 1 error, and we call that alpha. If we make the right decision under this, that would be 1 minus alpha, and this is our confidence level, isn't it? So this is the same as our confidence level here. And the type 2 error is beta. So we use beta for type 2 error. And that'll be a little confusing later because we're going to use beta in the next chapter for some parameters. But for when we're talking about error, beta is a type 2 error. So we've failed to reject H0 when H0 is false. And then this is our power. 1 minus beta is the power. And this is type 2 error. And this is type 1 error. Okay. So I want you to note something, that actually alpha and beta are related to each other. They're inversely related to each other. As alpha goes up, beta goes down. As beta goes up, alpha goes down. So we can't make both of them go down at the same time. So if we decrease alpha, which is what we'd want to do, unfortunately beta increases, and this is the caveat, unless we increase the sample size. So if n increases, then you can hold alpha constant and decrease beta. So sample size is very important. Okay. Now I also want to talk about something called the Bonferroni correction. If we perform more than one statistical test on the same data set, then the type 1 error is going to be greater than alpha. So because each individual test has a type 1 error equal to alpha, then you perform more than them and you end up getting something that's more than alpha. So the probability of at least one type 1 error is actually greater than alpha. So alpha gets inflated. So we can make a Bonferroni correction, and the pros are that if we're doing k test, k is a number, then we can use alpha over k as a type 1 error for each test, and we certainly won't exceed alpha for all the tests combined. The con to this is that the rejection region is so small that the power of each test is decreases. Okay, it may be too low to actually detect important deviations from H naught. So Bonferroni is what we call a little too conservative. So the solution is use power curves. This is an advanced topic that we'll talk about in Stat 333 or Stat 400. We will not talk about it in this class. So yes, you are welcome for that. Okay, so let's talk about sample size. So again, the only way that we can control type 2 error and type 1 error at the same time is to control our sample size. So if we have one population, we learned in Stat 222 that n will be greater than or equal to sigma hat times z alpha over 2 divided by e, which is our error. E is our margin of error. Okay, and notice that there's no consideration here for beta. Now, if we have two populations with the same sigma, and we'll learn in Chapter 5 why we're talking about only this case, because that's the only case we can deal with well in statistics, then n will be greater than or equal to, we've got z sub 1 minus alpha plus z sub 1 minus beta. So we add those two together. So now we're taking that into consideration. We're squaring it, and we're multiplying it by 2, and we're multiplying it by sigma hat squared. Now sigma hat squared is equal to s squared in most cases, okay, or some type of s. It may be for two, if it's two populations, it's going to be s sub p, which is our pooled sample variance. Okay, and divided by delta squared, and delta is the difference between mu1 and mu2 that we're testing for. So it turns out we can only calculate power for a specific alternative hypothesis, not all of them at once. So we can calculate alpha pretty easy or set it, but calculating beta requires that we choose a specific distribution and then calculate the probability with that. So here we've got a chi-squared distribution, and I'm not going to really go over this, and we've got F. These are some problems, but I'm not going to do this because we will talk about this when we actually get to those types of problems. I don't want to spend time now and then we forget when we get there. So when we get to those types of problems where we need to read the tables, we'll cover that at that time. Okay, some of you had me for Stat 222 last year or Stat 302. You know how to do this. So I put the answers in parentheses. So don't forget to scan your lecture notes by midnight of the date listed in the course calendar. So by midnight on that day, you know, these are for you, so be neat so you can read them. Update your formula sheet with anything you want from this. You know, the power, the confidence level, whatever, any tables that we looked at up above. If you have questions, please come to my virtual office hours. If those absolutely don't work for you, then by all means email me, and we will see you next.